What does it mean when a comet seems to breathe? That question started as a Whisper One late-night tweet from an astronomer staring at data that didn't make sense. It spread through observatories, Discord servers, and university Slack channels like wildfire. A comet, catalogued as 3I, the third interstellar object ever discovered, was exhaling water. Not gently sublimating as it neared the sun, but exhaling like a living thing in the cold silence of space. 40 kilograms of water every second. To put that in perspective, that's the equivalent of an entire car's weight in pure water, vanishing into vapor every minute. And it wasn't happening near the sun, where heat could melt or sublimate ice. No, this was taking place 3.5 times farther from the sun than Earth, out beyond the orbit of Mars, where sunlight is a whisper and comets sleep in frozen silence. Yet this one didn't. The discovery came from NASA's Swift Observatory, a satellite designed to detect gamma-ray bursts, the brightest explosions in the universe. But Swift's ultraviolet eyes are also perfect for spotting hydroxyl radicals molecules that appear when sunlight splits apart water vapor. On a quiet January morning in 2025, Swift turned toward 3I Atlas, expecting little more than a faint speck of reflected light. Instead, it saw a luminous halo, a vast ultraviolet cloud, glowing with the telltale signature of hydroxyl. And that could mean only one thing. There was liquid water vaporizing off this comet. Swift's data team double-checked the readings, then checked again. The signal wasn't faint, it was screaming. 1.35 times 10 to the power of 27 molecules of water per second. In mass terms, that's 40 kilograms every second. Out in the cold, airless vacuum where water has no business existing as anything but ice, it shouldn't have been possible. Comets within our solar system follow predictable rules. They're made of ice and dust, frozen remnants from the early solar nebula. When they approach the sun, solar heat causes their surface ice to sublimate to skip the liquid phase and go straight from solid to vapor, creating a glowing coma and tail. But far from the sun, there simply isn't enough energy to drive that process. At 3.5 astronomical units, the intensity of sunlight is less than 1/10 of what Earth receives. That's not enough to boil off even the most volatile ices. And yet, 3I Atlas was pouring water into space like a geyser. Astronomers began to whisper, this isn't supposed to happen. The object's very name, 3I Atlas, tells its story. 3I means the third interstellar visitor ever confirmed, following in the path of Oumuamua 2017 and Borisov 2019. Both of those earlier travelers rewrote parts of astronomy in their own ways. Oumuamua, the first, was dry, no tail, no coma, no gas, just a silent, tumbling shard of rock that sped past our planet without a word. Borisov the second behaved like a normal comet, icy, predictable, textbook physics. But 3I Atlas, it was something else entirely. Unlike its predecessors, this comet seemed alive. Its coma shimmered with oxygen fragments, cyanide, and carbon-based volatiles. It pulsed faintly, as if exhaling in waves. And its light curve, the measure of how its brightness changed over time, showed irregular surges, almost rhythmic, as though whatever process drove its outgassing wasn't constant, but cyclical. By early February, telescopes across the world had joined the hunt. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Lick Observatory in California all turned their instruments toward the intruder. The more they looked, the stranger it became. Spectroscopic analysis revealed that 3I Atlas's surface wasn't behaving like ice at all. The ratio of volatiles, water, carbon dioxide, cyanide was far beyond what's seen in typical comets. Even more puzzling was its temperature. The thermal data didn't line up with the amount of energy it was releasing. Something internal was driving this, some unseen heat source deep within. So scientists began asking questions that made them uneasy. Could chemical reactions inside the comet be generating heat? Exothermic reactions, say, of trapped gases or organics might explain the warmth, but that would require mobility of molecules within the nucleus, as if it were more porous and active than expected. Could there be super volatile ices like carbon monoxide or nitrogen, that evaporate at incredibly low temperatures? Possibly, but the observed emissions didn't match those fingerprints. And that's when someone half-jokingly said the thing everyone else was thinking. It's acting alive. The phrase stuck. Soon, YouTube channels and Reddit threads were ablaze with the term the breathing comet. It became a meme. Artists rendered 3-eye Atlas as a celestial organism, a frozen lung exhaling plumes of vapor into the void. Others went further, claiming it was artificial, or the remnant of a long-lost civilization. But for scientists, the mystery wasn't entertainment, it was existential. Because if 3-eye Atlas truly came from beyond our solar system, its chemistry, its structure, even its physics could reflect conditions in an entirely different star system, perhaps one richer in volatiles, or older, colder, and more complex than ours. And that idea that this object might carry the fingerprints of another sun was both thrilling and terrifying. By March, observatories had enough data to build preliminary models. What they found was a nucleus roughly 1.7 kilometers across, rotating every 9 hours, with jets erupting irregularly from specific regions. But those jets weren't correlating with sunlight exposure. In other words, they weren't triggered by day-night heating cycles. Something deeper was waking it up. Theorists proposed wild mechanisms: pressure buildup from trapped gases beneath layered ice, microfractures from rotational stress, or even the slow release of internal radioisotopes, decaying since the comet's birth billions of years ago. But none fit perfectly. Each explanation left gaps, and so the questions grew darker. If this was a natural process, why haven't we seen it before? If it's not, then what is it? At the Jet Propulsion Laboratory in Pasadena, a small team began coordinating with the European Space Agency to observe Atlas through ultraviolet and X-ray wavelengths. They wanted to see if the water emissions fluctuated in sync with solar radiation or magnetic fields. The answer came back inconclusive, but with a hint of something strange. The outgassing seemed to pulse at semi-regular intervals, roughly every 27 hours. Coincidence? Instrumental noise? Maybe. But coincidences like that have a way of keeping astronomers awake at night. Because sometimes the universe throws you something so far outside the pattern that it forces you to look again, not at the sky, but at your assumptions. And so, under the cold black canopy of space, an interstellar visitor began to teach us something we hadn't planned to learn: that even in the most frozen, lifeless places imaginable, activity can exist, not because it's alive necessarily, but because the cosmos is stranger, more dynamic, and more creative than we give it credit for. Still, no one could shake the feeling that 3-eye Atlas wasn't done surprising us. After all, water was only the beginning. And what came next would challenge not just our models of comets, but our understanding of where matter itself comes from. By the time astronomers thought they'd wrap their heads around the breathing comet, the universe threw another curveball. It came quietly, as most revolutions in science do, not in the form of a flashing headline or a viral tweet, but as a thin line on a spectrum. The data came from the Very Large Telescope in Chile, one of the most precise instruments on Earth. A group of researchers had pointed its high-resolution spectrograph at 3-eye Atlas to examine the wavelengths of light emitted by the gases streaming from its coma. Spectroscopy is the cosmic equivalent of fingerprinting. Every element leaves behind a signature, a set of sharp, unmistakable lines etched into the light it reflects or emits. Normally, when comets begin to shed metals, two friends always appear together, iron and nickel. They're cosmic siblings forged side by side in the hearts of dying stars, born in the same supernovae, locked together in the same mineral structures. When heat frees one, the other follows. It's a law of chemistry so consistent, it's practically a constant of nature, except not this time. When the VLT data came through, one of the senior spectroscopists thought her calibration was off. The nickel emission lines were blazing bright, distinct, unmissable. But iron, barely a whisper. The expected peaks were absent, like a choir missing half its voices. At first, the team assumed an error. Maybe the telescope's grating had shifted. Maybe the signal was contaminated by background noise. But no, the pattern repeated in observation after observation. Nickel, strong and clear, iron, missing in action. That wasn't a glitch. That was a message. Nickel without iron. To a chemist, that phrase is like hearing thunder without lightning. These two elements have almost identical condensation temperatures, meaning they vaporize at roughly the same point. In every known environment, planetary disks, meteorites, comets, even stellar atmospheres, their ratios remain stable. You can practically set your watch by it. So how was 3I Atlas producing nickel gas in abundance, while iron seemed absent? It shouldn't have been possible. 1 gram of nickel per second doesn't sound like much, but at the scale of a comet's coma, it's a torrent, a shimmering metallic fog streaming away from the nucleus. Over days, that adds up to tons of material, constantly replenished as the comet travels deeper into the solar system. And all of it apparently nickel. Scientists across institutions scrambled for explanations, Slack channels buzzed, check for calibration drift, rerun the solar subtraction. Maybe it's an instrumental artifact, but the pattern held. Observatories in Europe, South America and Japan all confirmed it. The emission lines at 341 and 356 nanometers pure nickel, if 3I Atlas was following known chemistry, those same emissions should have been mirrored by strong iron lines at nearby wavelengths. They weren't, so the theories began. The first hypothesis was fractionation, the idea that under certain exotic conditions, nickel and iron could separate during formation. Maybe billions of years ago in the nursery where this comet was born, something caused nickel to condense into volatile compounds while iron stayed locked in refractory minerals, heavier, less likely to vaporize. That could, in theory, explain why 3I Atlas releases nickel gas when it's barely warmed by sunlight, while iron remains trapped within its stony heart. But fractionation like that doesn't happen easily. It would require a disk environment rich in carbon monoxide and depleted in oxygen, a setting far different from our solar nebula. The second possibility was even stranger: organometallic compounds. On Earth, we've synthesized molecules like nickel carbonyl nicoke in laboratories. They're colorless, volatile and deadly, evaporating at incredibly low temperatures. If 3I Atlas's ices once mingled with carbon monoxide in a cold, carbon-rich environment, perhaps nickel atoms bound to CO to form such compounds naturally. When sunlight hit the comet, those fragile molecules could break apart, releasing pure nickel into the coma, while iron stayed inert, chemically imprisoned in solid grains. It was a fascinating idea and deeply unsettling, because if that were true, it meant this comet was not only carrying complex inorganic chemistry from another star system, but chemistry we recognize, chemistry that, on Earth, we only see in controlled laboratory reactions. A third theory emerged from cosmic weather itself: radiation processing. Over millions, perhaps billions of years, drifting through interstellar space, 3I Atlas would have endured relentless bombardment by cosmic rays and ultraviolet light. That kind of exposure can do strange things to surface chemistry, driving reactions that enrich one element while depleting another. Maybe the outer crust of the comet had become nickel-rich, a kind of metallic skin, while iron atoms got buried deeper or chemically altered into non-volatile forms. In that case, what we're seeing now might not reflect the comet's true composition, but a surface illusion, a scar written by radiation and time. But not everyone was convinced. The University of Cambridge, a group of astrophysicists, ran simulations using data from galactic chemical models. Their conclusion was bold. Maybe it wasn't chemistry at all, maybe it was cosmic ancestry. Not all stars are created equal. Some are richer in heavy elements than others, depending on which generations of supernovae seeded their birth clouds. The Sun, for example, was born from a well-mixed region of the Milky Way's spiral arm. But older stars, particularly those that fall near the galactic halo, often have unusual element ratios. If 3I Atlas came from such a system, a place where nickel was more abundant relative to iron, then its entire composition would reflect that difference. In other words, we weren't just looking at a weird comet, we were looking at the chemical fingerprint of another star. That possibility sent chills through the astronomical community. Because if it were true, then 3I Atlas wasn't merely an interstellar traveler. It was a messenger from a time and place where the universe itself followed different rules. A few skeptics pushed back. Maybe we're overinterpreting the data, they argued. After all, early spectroscopic readings can be misleading. Cometary activity is chaotic. A single jet, aimed just right, can skew emission ratios dramatically. But as weeks turned into months and more data rolled in, the nickel line stayed constant. Iron remained invisible. Patterns like that don't lie. By late April, several journals were preparing papers with cautious but revolutionary titles. Nickel enrichment without iron in interstellar comet 3I Atlas. Evidence for exotic fractionation mechanisms beyond the solar nebula. And in the footnotes of those papers, a quieter realization was taking root, one that scientists discussed only behind closed doors. If 3I Atlas truly came from a chemically distinct region of the galaxy, then our models of planetary formation might be incomplete. It would mean that what we consider universal, the shared chemistry of worlds, might actually be local. That's a staggering idea, because it implies that life, matter, and even the periodic table as we know it could vary from one corner of the Milky Way to another. It would mean that when we look up and imagine other worlds, we might be underestimating just how other they really are. And so, as astronomers stared at the glowing spectra on their screens, nickel lines burning bright where iron should have been a quiet tension settled in the air, skepticism wrestled with wonder, doubt with awe, and one sentence, spoken softly by a spectroscopist in Chile, captured the mood better than any press release ever could. Either our chemistry books are wrong, or 3I Atlas didn't form here. By late April, astronomers had already been forced to rewrite 2 chapters of the cometary rulebook. But 3I Atlas wasn't finished. It had one more revelation, one that would blur the line between poison and possibility. The first clue came from an observatory in northern Spain, perched high in the Sierra Nevada mountains. Astronomers there were scanning the comet's spectral output for signs of carbon-based volatiles, gases like carbon monoxide, carbon dioxide, HCO, and hydrogen cyanide, HCN. These are standard cometary compounds, relics from the time when the solar system was young. But what they found wasn't standard at all. 3I Atlas was saturated with cyanide. At first, the team assumed a calibration error. They cross-checked their data with another telescope in the Atacama Desert, same result. The comet's coma, the luminous haze surrounding its nucleus, was glowing with the spectral fingerprint of the cyanogen radical CN. That's what cyanide becomes when ultraviolet sunlight tears apart hydrogen cyanide molecules, leaving behind a single carbon atom bound to nitrogen, glowing faintly blue. In the language of spectroscopy, CN is the voice of organics. When you see it, you know carbon chemistry is at play, but the sheer abundance around 3I Atlas didn't make sense. The signal was several times stronger than in any known comet, even those close to the Sunday. This object wasn't just releasing cyanide, it was bleeding it. To most people, cyanide means poison, the stuff of spy novels and dark history, a compound so lethal that a few milligrams can silence life in seconds. It binds to the iron in hemoglobin, choking cells of oxygen. On Earth, cyanide is death, but in space, cyanide might be something very different. Because among chemists who study the origins of life, cyanide is paradoxically precious. It's a molecular multi-tool, reactive, adaptable, capable of stitching together the complex building blocks of amino acids, nucleotides, and sugars. In laboratory simulations of the early Earth, cyanide chemistry has been shown to produce the precursors of RNA, the first genetic molecules. So when astronomers detect CN in a comet, it's not just a signal of toxicity, it's a hint of prebiotic chemistry. The same molecules that kill life on Earth may once have helped create it. But here's where 3I Atlas defies comprehension. This comet wasn't just carrying cyanide as a trace compound, it was dominated by it. Its cyanide to water ratio was off the charts, several times higher than anything measured in comets like Halley or Hale-Bopp. And this wasn't even a solar system body. This was an interstellar visitor, forged around another star, carrying within it the seeds of chemistry that may have unfolded light years away, long before Earth existed. The implication hit hard. If cyanide-based organics form naturally in other planetary systems, if they're common rather than rare, then the chemistry of life might not be unique to our corner of the galaxy. The European Southern Observatory confirmed the results in early May. Using their high dispersion spectrograph, they resolved not just CN, but a faint halo of C2 diatomic carbon, another hallmark of organic breakdown. That combination, CN and C2, is the unmistakable signature of complex organic material being vaporized and destroyed by sunlight. In other words, 3I Atlas was carrying carbon chains, maybe simple hydrocarbons, maybe polymers that were now disintegrating as it approached the Sunday. And yet it was doing so at a distance where sunlight shouldn't have enough energy to trigger such chemistry. Another paradox, another breach in the rulebook. Across universities and observatories, scientists started to piece together the puzzle. What if 3I Atlas wasn't just composed of volatile ices and silicate dust, but organic tar, the dark, carbon-rich residue of chemical evolution that happens on the surface of icy grains in deep space? We've seen this before, faintly, in samples from the Rosetta mission's visit to Comet 67P Churyumov-Gerasimenko. Its dust was laced with amino acids and simple organics. But those molecules formed within our solar system. 3I Atlas was different. It came from somewhere else entirely, a place where cyanide chemistry might have run its own ancient course, possibly under a different star's radiation, maybe even within a completely different chemical balance of elements. Some of those organics, forged in alien conditions, were now burning off in the light of our sun chemical ghosts of another world. The thought left researchers silent, because if this comet truly formed billions of years before our solar system, then some of the molecules inside it could be older than Earth's oceans, older than the sun itself. Fragments of molecular evolution from a time when our galaxy was young, drifting now into our backyard to whisper its story in ultraviolet light. But not everyone was romantic about it. When the results were published, skeptics were quick to point out that cyanide signatures are tricky. CN can form from several parent molecules, not just HCN, and the interstellar medium itself is rich in it. Some argued that interstellar dust coating the comet's surface might be contributing to the readings. Others suspected contamination from background gas in the telescope's line of sight. Still, the data consistency was unnerving. Independent instruments, separate hemispheres, identical results. Something on 3I, Atlas was producing an ocean of cyanide gas. And with every new observation, the comet's symbolism deepened. To some, it became a symbol of life's universality proof, that organic chemistry thrives across the cosmos. To others, it was a darker omen, a harbinger of how fragile that same chemistry can be. A comet leaking, the chemical of death, and maybe the blueprint of life. The public fascination exploded. Memes labeled it the death comet, while astrobiology channels on YouTube called it the Genesis engine. The irony wasn't lost on anyone, a cosmic traveler exhaling poison that could also be the seed of creation. In late May, a group of researchers at the Max Planck Institute ran infrared models showing that 3I Atlas's cyanide emission correlated with periodic increases in brightness, a pulsing effect, like the comet was breathing again, but this time not water life's dark twin. And there was one final twist. Using polarization data, astronomers noticed that the light reflected off the comet's tail had an unusual scattering pattern consistent with long-chain organics, carbon molecules stretching dozens of atoms long. These were complex, carbon-rich materials, the kind that, on Earth, can form in soot, petroleum, or even biological decay. 3I Atlas wasn't just exhaling volatile gases, it was shedding the chemical story of a world we've never seen. Maybe a world that never made it a protoplanet destroyed before it could form its molecular fragments scattered across interstellar space. Or maybe something else, something that once flourished under a forgotten sun and has now drifted across time and darkness to find us. As scientists debated, one quote began to echo through astronomy circles, attributed to a planetary chemist in Munich who had spent weeks staring at the spectral data. If you stare long enough into this comet's tail, it feels like it's staring back, asking us what we think life really means. It's a haunting thought, because cyanide is both death in creation, the end of breath and the beginning of chemistry. And 3I Atlas, this wandering shard from another star, seems to carry both truths at once. What it's telling us, we still don't know. But one thing is certain: whatever star gave birth to 3I Atlas, whatever ancient system scattered it into the void, it left behind a warning, or perhaps a gift, written not in words, but in molecules. And those molecules have finally reached us. When you hold a piece of a comet in your hand, or rather, when a spacecraft's spectrometer does, you're holding time. Not just a sample of rock or ice, but a chemical timestamp. Ratios of isotopes, the slightly heavier or lighter versions of familiar elements, act like fingerprints left by the stars that forged them. And in June, when astronomers began analysing the isotopic data from 3I Atlas, the fingerprints didn't match anything in the solar system. The data came first from the Infrared Telescope facility in Hawaii, then confirmed by ALMA in Chile. They had been comparing isotopic ratios of carbon, nitrogen and oxygen, specifically the relative abundances of bean squared C to demi cart C to bean quart N to demi cart C and N to tot CO to demi cart CO. In our solar system, these ratios are remarkably consistent. Every comet, asteroid, planet and gas cloud shares the same broad chemical ancestry, all forged from the same molecular cloud that birthed the Sun 4.6 billion years ago. But 3I Atlas was an outsider, and its chemistry screamed it. Its nitrogen isotope ratio was wildly offset. Double Wien 4 to N divided by double Wien 4 to N equals 140, compared to Earth's 272. Oxygen was even stranger. The double wing 4 divided by double wing 4 ratio matched no known solar or pre-solar body. It was as if the atoms in 3I Atlas had been forged in a furnace that no longer existed. "Nothing in the solar system looks like this," said Dr. Karine Deveau, an astrochemist at the Institut d'Astrophysique de Paris. You're looking at material that predates the Sun, literally older than the solar neighbourhood itself. The words sent a chill through the community. Because if those isotopic signatures were real, then 3I Atlas wasn't just an interstellar comet, it was a relic of galactic prehistory. In essence, a fragment of the universe's adolescence, wandering ever since. The next phase was dust analysis. Using polarization data and mid-infrared spectroscopy, astronomers reconstructed the composition of the comet's solid particles. What they found deepened the mystery. The dust grains were rich in amorphous silicates, uncrystallized glassy minerals that form only in extremely cold, radiation-shielded environments. Some contain traces of presolar grains, tiny specks of material that can be dated to before the Sun's formation. These grains bore the isotopic hallmarks of Type II supernovae, massive stars that exploded billions of years ago, long before our solar system's molecular cloud ever condensed. If the models were correct, 3I Atlas likely formed from the debris of one of those early stellar deaths, perhaps in a cluster of stars that has long since dissolved into the Milky Way's spiral arms. Which means this comet might not just be older than our Sun, it could be older than our galactic neighbourhood. When news of the isotopic anomaly broke, it forced astronomers to think on a cosmic scale. We like to imagine comets as local relics, cold archives of our own solar system's formation. But 3I Atlas shattered that illusion. It wasn't a page from our story. It was a fragment from another book entirely. To imagine its origin, scientists turned to galactic archaeology, the study of how stars and planetary systems have evolved across the Milky Way's 1-3 billion year history. They simulated clusters of young stars forming in dense molecular clouds, the cradles of creation. In those simulations, some stars grew quickly, went supernova, and scattered their elements into space. Others, like our Sun, formed later from that enriched dust. But in the chaos, some leftover debris, icy planetesimals and comets were flung outward at interstellar speeds, escaping their home systems forever. Over billions of years, those fragments drifted between the stars, caught in the galaxy's slow rotation, becoming what astrophysicists now call galactic orphans. 3I Atlas, it seemed, was one of them. For the first time, humanity was studying one of those orphans up close, a shard of chemistry from before Earth existed. When scientists modelled its trajectory backward, they found that 3I Atlas might have wandered interstellar space for over 5 billion years, long enough to cross spiral arms, pass through molecular clouds, and survive the radiation of countless nearby supernovae. It has seen stars born and die. It had watched civilizations rise and vanish, unseen from the void, and yet, through all that time, it remained frozen, untouched, a perfect molecular time capsule. To hold something older than the sun is to confront a strange vertigo, a sense that time itself has folded in your hand. Because in that dust are atoms that once danced in the heart of a star that exploded before the Earth was even an idea. As one researcher put it, 3I Atlas is not from another solar system, it's from another epoch. This realization transformed the comet from a curiosity into a kind of messenger. Its chemistry, its anomalies, the nickel without iron, the cyanide tail, the strange isotopic ratios weren't random, they were memories. Each one encoded a piece of cosmic history written before our own sun began to shine. In the lab, scientists began comparing 3I Atlas's spectral fingerprints to samples collected from ancient meteorites, especially those that still contain pre-solar grains, like the Murchison meteorite that fell in Australia in 1969. To their astonishment, some isotopic patterns matched, the same Type II supernova signatures, the same nitrogen anomalies. It was as if 3I Atlas had been forged in the same galactic neighborhood where those early meteorites' parent dust was born, a region that existed long before the sun, now long gone. The poetic and the scientific began to blur. Journalists wrote of a ghost from before the Sunday. Planetary scientists called it a comet made from the ashes of dead stars. But perhaps the most haunting description came from a NASA astrobiologist. 3I Atlas is like a fossil from before the Earth had oceans, before there was even an Earth to have them. It's what the universe looked like before it knew how to make life. Late that summer, as the comet drifted away from the sun and began its long, cold exit back into the interstellar dark, the data kept coming in. Its surface cooled, its outgassing faded, and the cyanide glow dimmed into silence. But the memory of it, the knowledge of what it carried, lingered like a whisper from deep time. For all we know, it may have been one of countless such travelers, slipping silently through the galaxy, relics of forgotten stars, still carrying the chemistry of creation, each one older than our Sunday, older than the light that touches them, each one a messenger from an age before memory. In the quiet that followed its departure, one question remained. If something that old can find its way here across billions of years and endless dark, what else might be out there, still waiting to be seen? At first, astronomers thought the numbers were wrong. They had to be. When the first orbital models of 3I Atlas were published, the data looked clean. A steep hyperbolic trajectory slicing through the solar system, inbound from the constellation Sculptor, outbound toward the dark between stars. The inclination was odd, but still plausible. The speed, about 26 kilometers per second, was high but not impossible. Everything about its motion seemed perfectly ordinary for an interstellar interloper. Until it began with residuals, the faint mismatches between where the comet should have been and where telescopes actually found it. In orbital mechanics, those residuals are the equivalent of a heartbeat, small pulses that tell you whether your math matches reality. For most comets, the deviations come from outgassing. As sunlight heats their surfaces, jets of vaporized ice act like tiny thrusters, subtly changing their paths. These non-gravitational accelerations are well known, predictable, and usually fade as the comet moves farther from the Sunday. But 3I Atlas was different. Its deviations weren't fading, they were growing. By mid-May, when the comet was nearly 3.6 astronomical units from the Sun, far too cold for significant sublimation, it began to drift off its expected course. The discrepancy was small at first, just a few arc seconds, then tens, then hundreds. The comet wasn't where Newton said it should be. NASA's Jet Propulsion Laboratory quietly released an updated trajectory, but the fine print in the model noted an unexplained non-gravitational acceleration vector inconsistent with solar outgassing. Translated, the comet was moving as if being pushed by something no one could account for. The easy answer was asymmetrical jets localized outgassing from one side of the nucleus, like a poorly balanced rocket. But that explanation hit a snag. The magnitude of the deviation didn't match the comet's observed activity. Even at its most active, the water and gas flow from 3I Atlas wasn't nearly strong enough to produce the measured acceleration. In fact, to account for the observed shift, the comet would have needed to be venting 10 times more mass than telescopes actually saw. So either the observations were incomplete or the comet was being pushed by something invisible. Astronomers at the European Space Agency ran new simulations. They adjusted for thermal lag, surface topology, rotation rates. Nothing fit. The direction of acceleration didn't line up with sunlight exposure or spin orientation. Instead, the force seemed to track a fixed vector one that rotated with the comet's position relative to the Sunday. That shouldn't be possible. One physicist at the University of Bern half-jokingly called it the whisper thrust, as if something about the comet was continuously steering itself ever so slightly, in ways the math couldn't explain. Online forums erupted. Theories poured in. Some invoked outgassing from exotic ices like carbon suboxide or nitrogen trapped in clathrates, compounds that can sublimate even in deep cold. Others speculated about electrostatic forces, solar wind coupling, or magnetic field interactions. And then, inevitably, came the stranger ideas. What if the motion wasn't natural? It wasn't the first time astronomers faced this kind of riddle. Years earlier, Oumuamua, the first confirmed interstellar visitor, had displayed a similar anomaly, a tiny but measurable acceleration that couldn't be explained by visible outgassing or radiation pressure alone. At the time, some researchers proposed it might be a fragment of a light sail, a thin, reflective sheet propelled by sunlight. The idea was dismissed as fanciful, but it lingered in the public imagination. Now, 3I Atlas seemed to be echoing the same enigma, only bigger, wetter, louder, and with data too solid to ignore. At Caltech's Orbital Dynamics Lab, researchers fed all available measurements into their integrators. When they subtracted out known gravitational influences, the Sun, planets, and even subtle tugs from Jupiter and Saturn, there was still an unexplained acceleration of roughly 4 times 10 to the power of -7 meters per second squared. That's minuscule, about 100 millionth of Earth's gravity, but sustained over months, it was enough to alter the comet's path by thousands of kilometers. And the vector pointed away from the Sunday. Not random, not rotating, directed, almost intentional. One paper from a group at Kyoto University dared to ask the question others avoided. What if 3I Atlas's motion isn't just reactive, but regulated? The idea wasn't that it was controlled in the science fiction sense, but that some physical mechanism, maybe electromagnetic, maybe quantum mechanical, was damping or amplifying its motion in a feedback loop. If that were true, it could explain both the anomalous acceleration and the strange consistency of its water outgassing. But it also opened a door few were comfortable walking through. The possibility that interstellar bodies might exhibit behaviors with mistake for control-guided motion, not by intention, but by physics we don't yet understand. NASA's official stance was cautious. In a briefing, they referred to the anomaly as non-Newtonian accelerations consistent with unknown surface processes. But behind the scenes, emails later obtained through FOIA requests showed clear frustration. One engineer wrote, "We can't reconcile the JPL fit with the photometry. Something's off by orders of magnitude." Another, "We're seeing a residual that shouldn't exist unless there's a distributed mass anomaly." In plain terms, either the comet's density distribution was impossible, or gravity itself wasn't telling the whole story. Meanwhile, the Deep Space Network noticed something odd. The reflected radar echoes from 3I Atlas didn't return exactly where expected. There was a lag, a subtle Doppler mismatch that suggested micro-oscillations in velocity, as if the comet were pulsing, gently adjusting its speed. The data was clean. The effect was real. The cause? Unknown. That's when the more speculative models started circulating, what some call the guided motion hypothesis. It proposed that interstellar comets like 3I Atlas could contain subsurface materials that interact with the interplanetary magnetic field, generating Lorentz forces strong enough to subtly steer them. Essentially, the comet might behave like a self-induced plasma sail, an unintentional navigator of electromagnetic seas. It sounded wild, but the math worked. If the nickel emission and strange chemical asymmetries altered the comet's magnetic permeability, solar plasma could indeed exert a directional force, small but continuous. And suddenly, everything lined up. Of course, there was a more unsettling possibility. If 3I Atlas had travelled for billions of years, shaped by alien chemistry and ancient physics, perhaps its materials respond to the universe in ways ours don't. Maybe its motion isn't a mystery of control, but of composition, a side effect of matter built under a different rule book. The question wasn't whether something was pushing it. The question was whether we even understand what it means to be pushed. In the final reports submitted to the Minor Planet Center, the official explanation remained conservative. Non-gravitational perturbations consistent with asymmetric volatile outflow. But off the record, the scientists who ran those fits would say the same thing when the cameras were off. It's not following the map. By autumn, 3I Atlas had begun its outbound journey, but the debate was far from over. The chemical mysteries had drawn headlines, but this, the impossible trajectory, haunted the quiet back rooms of observatories everywhere, because the math wasn't supposed to lie. And yet, here was a comet that seemed to rewrite the laws of motion, 1 kilometer at a time. The universe, it seemed, was whispering a reminder that even gravity, the most familiar force of all, might still have secrets left to tell. October arrived, like a cosmic convergence, a month when coincidences began to feel like choreography. By then, 3I Atlas had already carved its name into every late-night astronomy thread, every fringe science podcast, every speculative corner of the internet. It was the comet that breathed, the comet that defied Newton, the comet that seemed to rewrite chemistry. But as the leaves turned and the skies over the northern hemisphere deepened into autumn, another layer of strangeness began to unfold. Because on the night of October 8th, Mercury, Ceres, and 3I Atlas lined up across the dawn horizon in a rare celestial arrangement that hadn't occurred in over a century. And that same week, a group of citizen radio astronomers stumbled upon something else entirely, an unexplained series of expanding radio halos in deep space. Massive, perfectly circular, growing. They called them odd radio circles, or orcs. And suddenly half the internet decided the sky was trying to tell us something. At first, the alignment seemed like an astronomical curiosity, nothing more. Planetary conjunctions happen all the time. Mercury zips around the sun every 88 days. Ceres, the largest object in the asteroid belt, takes 4.6 years. Their orbits occasionally cross in our line of sight, forming a visual echo of alignment. But adding 3I Atlas into the mix was what sparked attention. The geometry was eerie. From Earth's perspective, the three objects traced a near straight line through the constellation Virgo, less than 2 degrees apart in apparent motion. The comet's faint, cyanide-laced tail stretched like a thread across that same alignment, a silver-blue arc visible in long exposure images posted by amateur astronomers across Europe and Asia. By morning, those images had gone viral. Number 3I alignment trended on X. TikToks and YouTube shorts filled with ambient music and captions like "something cosmic is happening." For a brief moment, science and superstition blurred in the public mind. And then came the radio anomaly. In Australia, members of a volunteer network known as Radio Skywatch had been scanning low-frequency bands for transient emissions. Their antennas picked up a faint, circular distortion, a ghostly ring of radio noise stretching across nearly a degree of sky. At first, they thought it was an artifact, a calibration error, but within 48 hours, the same pattern was confirmed by other independent stations in South Africa, Chile, and Spain. They weren't glitches, they were real. Enormous faint halos of radio emission expanding slowly, symmetrically, as if something in the deep dark had detonated a ripple through space itself. This wasn't entirely unprecedented. Astronomers had first discovered ORCs back in 2019 using the Australian Square Kilometre Array Pathfinder. At the time, they had no explanation. Theories ranged from shockwaves from galaxy mergers to the remnants of ancient radio jets. But the timing, the alignment with 3i, Atlas, Mercury and Ceres reignited public fascination, especially when one of the new oaks appeared to be projected along the same celestial coordinates as the comet's outbound path. Coincidence? Probably. But coincidence rarely stops curiosity. By mid-October, astronomy forums were flooded. On Reddit's r/space, a user posted, "So 3i, Atlas, Mercury and Ceres line up, and we suddenly detect the biggest ORC ever seen, 6 million light years across, along the same RA. Deck as the comet's trajectory. What are the odds?" Replies flooded in. Just coincidence. Everything aligns with something, unless it's signaling. Conspiracy threads exploded overnight. Some linked it to the Voyager 1 signal dropouts happening the same week. Others claimed the ORCs were gravitational echoes caused by the comet's non-Newtonian motion. Few went further still, suggesting they were responses, messages returning from whatever 3i Atlas came from. Even mainstream outlets couldn't resist the story. The BBC ran a cautious headline: "Celestial coincidences, Mercury, Ceres, and a mysterious comet align as radio rings emerge." CNN called it a week of cosmic strangeness, but it was Sky and Telescope that struck the most poetic tone. For a brief moment in October, the solar system seemed to hum in harmony, 3 bodies, 1 path, and a whisper from the deep sky. The truth, of course, was less mystical, but no less fascinating. Radio astronomers analysing the ORC data soon confirmed that the phenomenon wasn't local. These were extragalactic structures, millions of light years wide, their emissions dating back hundreds of millions of years. No connection to 3i Atlas, no strange new signal, just a case of cosmic serendipity, the kind that feels scripted only because our minds crave pattern. And yet, the timing still gnawed at people. It wasn't just that these events happened together. It was that they happened under a sky already primed with mystery, a sky haunted by a comet that breathed water in the cold, bled nickel without iron, and refused to obey the laws of motion. When the universe already feels uncanny, coincidence starts to look like design. Back at the professional observatories, astronomers were too busy to chase the hype. They were running orbital refinement models, cross-checking spectral data, and trying to explain why 3i Atlas's coma polarization didn't match known dust geometries. But in the background, they noticed something odd too, a faint uptick in solar radio noise, a temporary rise in interplanetary scintillation, like the solar wind itself was vibrating differently during the alignment, just enough to make people wonder. In the online chaos, one post cut through the noise, a detailed blog entry by an amateur named Alexi Navarro, a Spanish electrical engineer turned astrophotographer. He overlaid the ORC detections with the October alignment, calculating the angular separations and timing offsets. His conclusion was simple but chilling. Statistically, these events should not coincide by chance more than once in 20,000 years. The claim wasn't peer-reviewed, it wasn't precise, but it spread like wildfire. Soon, podcasts, YouTube breakdowns, and TikTok compilations were quoting it as gospel. The 20,000-year alignment, the cosmic coincidence that woke the world. And 3 Eye Atlas, already a comet of impossibilities, became something else entirely, a symbol. Across forums and live streams, the tone shifted. People began to speak of the sky not as something distant, but as something active, alive. First, the comet breathes, one viral post read, then the universe answers. It didn't matter that scientists found natural explanations for every piece of it. The deeper truth was psychological. When we peer into the cosmos and see strangeness reflected back, we feel a kind of dialogue, as if reality itself has started to whisper. And in October 2025, the world was listening. In the end, astronomers moved on. The orcs were mapped, catalogued, explained. Mercury and Ceres continued their quiet revolutions. The comet faded, dimmer each week as it left our skies behind. But for millions of people, the night watchers, the forum lurkers, the dreamers who looked up that month, something had changed. They'd glimpsed, for a fleeting moment, the illusion of cosmic synchronicity. And maybe, just maybe, it wasn't an illusion at all. By late October, the sky was still bright, with 3 Eye Atlas, a ghostly streak just beyond Mars's orbit, receding into the dark. But on Earth, the conversation was fading for another reason entirely. NASA went quiet. At first, it was subtle. A missed press release, a delayed live stream. The kind of bureaucratic pause that happens when departments get tangled in scheduling. But within days, the silence thickened, spreading through official channels like fog. The comet that had captured the world's imagination suddenly disappeared from the agency's communications. And the people who noticed first weren't scientists, they were journalists. On October 19th, the Atlantic Science Desk had been preparing an article titled 3 Eye Atlas, the comet that shouldn't exist. The journalist, Rebecca Yoon, had been in touch with the Jet Propulsion Laboratory's press office for weeks. She had quotes lined up from mission analysts, a timeline of spectral findings, and even a preview of NASA's next public briefing. Then, 2 days before publication, her contacts stopped replying. Emails bounced back with automatic replies, out of office. Phone lines went to voicemail. The scheduled briefing for October 21st was postponed indefinitely due to internal review. Yoon described it later in an editorial. It felt like watching a window slowly frost over. 1 week we had full transparency, then nothing. It was as if someone had flipped a switch labelled silence. Even NASA's own Horizons orbital data feed the automated system that tracks every known body in the solar system began showing unusual gaps. 3 Eye Atlas's coordinates were still listed, but updates lagged by hours, then days. The comet's predicted trajectory stopped refreshing altogether for nearly a week. Technically, the data wasn't classified. It was just missing. When pressed, a NASA representative gave a short, almost robotic statement. Routine recalibration of small body ephemerides is underway. Data will resume shortly. But it didn't. And in the silence, the internet filled the void. On Twitter, astronomers began whispering in code. At Astromason, a postdoc at Caltech, tweeted, "Strangest week of my career. Models don't line up, people stop talking, meetings cancelled. Never seen anything like it." Then deleted the post 12 minutes later. Another user at Lunar Pulse posted a screenshot from the Minor Planet Center's server logs, timestamps missing for 3 Eye Atlas uploads, replaced by placeholders reading withheld, awaiting verification. Even the European Space Agency's ESA Gaia team, usually quick to publish parallax updates, suddenly paused their comet-related releases. The chatter grew feverish. Reddit threads multiplied. NASA's hiding something. JPL locked down their 3 Eye datasets. Internal dispute over origin, possibly artificial. Most of it was nonsense. But not all of it. A freelance science journalist named Michael Donoghue, who'd been covering interstellar objects since 2017, reached out to one of his contacts inside Ames Research Center. He asked bluntly, why the radio silence? The reply came not through email, but as a text message from an unlisted number. It's not what you think. They just don't agree on the data. Half the team says the acceleration is instrumental noise, the other half says it isn't. And no one wants to be wrong, not after Oumuamua. Donahue pressed for more, but the source went dark. He published a short article on his Substack anyway. The disagreement inside NASA. It went viral overnight. Inside the agency, there really was tension. A leaked internal memo, later verified by multiple journalists, revealed that the Small Bodies Program Office had entered a review period to reconcile inconsistencies in outgassing force models and anomalous light curve residuals. In simpler terms, the comet's motion didn't match expectations, and the math wasn't adding up. One faction, primarily orbital dynamicists, believed the small deviations in trajectory were caused by standard sublimation jets of vapor, pushing the comet slightly off course. But others pointed to something stranger. The deviations weren't random. They followed a pattern, a series of micro-accelerations that seemed to pulse every 26 hours, almost rhythmically. And when a team from the Goddard Space Flight Center proposed that the periodicity might indicate internal oscillations or even an unknown form of mass ejection, the discussion reportedly became contentious. So the decision was made. No more public statements until internal consensus was reached. For the public, the silence felt conspiratorial. For the scientists inside, it was humiliating. A young astrophysicist, speaking anonymously to Nature, described the mood like this: "Everyone's afraid of another media circus. Last time, with Oumuamua, half the internet thought it was an alien probe. Now we have an object even stranger and we can't explain it. So we're told to pause, verify, and keep quiet. But silence only makes the noise louder." The article was quickly retracted, but screenshots survived. By early November, the blackout reached absurd levels. NASA's official Eyes on the Solar System app removed the comet from its live visualization altogether. Searches for 3I Atlas returned no current data available. Meanwhile, the Pan-STARRS Observatory in Hawaii, which had been one of the first to image the object, suddenly listed its follow-up datasets as restricted pending review. The world's biggest space agency seemed to have collectively looked away. And yet, independent observatories continued to publish images. The comet was still there, gliding silently past the orbit of Mars, its faint turquoise tail shimmering against the stars. It hadn't gone anywhere. Only the words had. In absence of NASA's voice, others filled the void. The YouTube channel called CosmoLeak uploaded a viral video titled NASA's 3I Atlas Cover-Up Explained. It featured leaked snippets of internal audio, later proven fake, of scientists arguing about anomalous propulsion. TikTokers stitched telescope footage with eerie synth music whispering. They don't want us to know what's out there. And while most of it was clickbait, the real consequence was deeper, a growing fracture between the scientific establishment and the people who once trusted it. Then, just as suddenly as the silence began, something else happened. On November 3rd, NASA's official Twitter account posted a brief, sterile update. 3I Atlas remains under observation. Preliminary analyses continue. No unusual findings to report at this time. It was the kind of statement meant to calm a storm, but instead it only proved there had been one, because the silence had already said enough. In hindsight, it's unclear whether NASA's pause was driven by caution or confusion. What's certain is that something fractured in those weeks, not in the data, but in trust. The world had glimpsed an object that defied explanation, and the institutions built to explain the universe had gone mute. And so, once again, the public turned their eyes to the independent voices, the rogue observers, the citizen scientists. If NASA wouldn't speak, perhaps the cosmos would, in its own way. When science goes silent, imagination gets loud. In the weeks after NASA's communications blackout, the search for answers drifted from labs to living rooms to basement observatories, Discord servers, and late-night live streams where amateur astronomers pored over gigabytes of data looking for something, anything. And that's when the patterns began to appear. It started innocently with a Reddit post. A user named U Orbital Echo shared a spectrogram from the Allen Telescope Array, one of the few public-facing radio observatories still streaming live data. The plot looked like random noise streaks of static across the frequency domain, but at the far edge, near the hydrogen line, faint rhythmic bands pulsed every few seconds. The caption read, "Anyone else seeing these repeating harmonics near 1,420 MHz looks too regular to be interference." At first, no one cared, but then others began uploading screenshots, different observatories, different times, the same faint pattern. Every few seconds, a pulse. Not a beep, not a signal, just a structure. One commenter summed it up. "It's like something whispering through the noise, not words, but rhythm." Within a week, the post had over 50,000 upvotes. Scientists were quick to dismiss it. The SETI Institute released a statement calling the harmonics instrumental artifacts the result of overlapping telescope networks and data compression. But even as they reassured the public, they quietly started checking, because the pattern didn't match known forms of radio interference, not satellites, not Wi-Fi leakage, not cosmic rays. It was too precise, too patient, and its strength waxed and waned every 26 hours, the same periodicity that NASA's internal data had been debating just weeks earlier. Coincidence? Probably, but coincidence has never stopped curiosity. Soon, YouTube channels were comparing the repeating pulses to odd radio circles, enormous ring-shaped structures discovered years earlier in deep radio surveys. No one truly understood what created them, though theories ranged from supernova shockwaves to the afterglow of black hole activity. But the timing was eerie. The ORCs had flared brighter. The same month, 3I Atlas entered our solar system. And now, the rhythmic radio pulses, faint but global, seemed to echo the comet's rotational cycle. The idea spread like wildfire. Was 3I Atlas resonating with something in deep space? This is where the line between science and pattern seeking blurred into something more human. Humans have an ancient habit to see faces in clouds, gods in stars, purpose in chaos. It's called pareidolia, the brain's craving for meaning where none may exist. We heard messages in the hiss of early radio static. We saw canals on Mars where there were none. We imagined music in cosmic background radiation. And now, in the static of the stars, we thought we heard a pulse. It wasn't the first time, but it was the most tantalizing. A linguist from MIT, Dr. Rowan Innes, wrote a viral essay titled "The Syntax of Noise." She argued that maybe communication didn't have to mean words, that a pattern itself could be a kind of message. "We think in binary," she wrote, "expecting language to be structured like ours. But if a civilization spoke through resonance, if it used energy itself as syntax, would we even recognize it as speech?" Her essay became a manifesto for a new kind of cosmic optimism, the idea that maybe the universe was speaking, just not in a dialect we understood. Still, most scientists remained skeptical. At the Harvard-Smithsonian Center for Astrophysics, researchers ran simulations showing that repeating harmonics could easily arise from resonant scattering radio waves bouncing between plasma fields in interstellar space. The 26-hour modulation, they suggested, might be caused by Earth's rotation relative to the comet's tail, creating a beat frequency illusion. In other words, a trick of perspective. The cosmos wasn't talking. We were hearing echoes of our own motion. But not everyone was convinced. At the Atacama Large Millimeter Array in Chile, a graduate team led by Sophia Martins took a closer look. They cross-referenced the harmonic frequencies with spectral data from the comet's coma, the cloud of gas surrounding its nucleus. To their astonishment, they found something strange. The hydrogen cyanide emissions CN bands fluctuated in near synchrony with the radio pulse intensity. When the pulse brightened, so did the cyanide signal. Martins described it in a private notes, later leaked online. Either the comet's chemistry is oscillating with remarkable regularity, or something external is modulating its emission. The note ended with a single line: "It feels alive." That phrase caught on like wildfire. The comet that breathes. the signal that beats, the message in the static. Podcasters dissected every spectrogram frame by frame. Some claimed to see encoded ratios in the spacing of the pulses, prime numbers, Fibonacci intervals, harmonics of hydrogen resonance. Others pointed out that humans are masters of finding structure in randomness. Given enough data, we'll see patterns even in noise because we're wired to. It's how we survived, how we built myths from stars. Yet amid all the skepticism, there lingered one quiet, unnerving fact. No one could fully explain the synchronization between the comet's outgassing and the radio harmonics. Coincidence or communication, the data refused to settle. In one of her final blog posts before her research was taken offline, Martens wrote, "Perhaps we've been listening the wrong way. Maybe messages aren't sent to us, maybe we simply drift through them, like insects through radio waves. Perhaps 3i Atlas isn't sending anything, perhaps it's reacting to something we can't yet see." The words resonated metaphorically and literally. Because as 3i Atlas drifted further from the sun, the pulses began to weaken. The harmonics faded back into background static. The comet, it seemed, was quieting, and with each passing day the silence returned, but it wasn't the same silence as before. It was heavier now, charged with implication. As if the universe had cleared its throat, whispered something unfathomable, and then just as quickly gone still again. In the end, no one agreed on what it was. SETI called it noise. Independent astronomers called it resonance. The internet called it proof. But somewhere between science and story, between chaos and pattern, the mystery of 3i Atlas deepened. Because even if the signal wasn't real, the idea of it was that in the endless hiss of the cosmos, we might not be alone in listening. It began with a glint, a shimmer no one expected. By late October, 3i Atlas was past its perihelion, receding into the outer dark. Yet its light curve, the way it reflected sunlight, refused to behave like any known comet. Instead of fading smoothly as it moved away from the sun, its brightness fluctuated, pulsing with an almost mechanical rhythm. At first, astronomers chalked it up to rotation. Maybe the comet was tumbling, exposing different facets of reflective ice. That's normal. But when photometric models tried to reproduce the pattern, something broke. The brightness wasn't varying randomly, it was modulating with intentional symmetry. Every 7.2 hours, the light reached a precise peak. Every 7.2 hours, it dimmed again with clockwork accuracy. Natural bodies wobble, they flicker, they shed dust, they act chaotic. But this was choreography. The first to notice the anomaly was Dr. Hana Suzuki, working from Japan's Subaru telescope. Her team had been monitoring the comet's albedo, how much sunlight it reflects, and found that 3i Atlas wasn't just unusually bright, it was directionally bright. When light struck it from certain angles, the reflected intensity spiked, as though the surface were made of tiny, aligned mirrors. Suzuki's report described it in clinical terms. The surface scattering function suggests multi-layered anisotropic reflection inconsistent with homogeneous icy composition. In simpler words, it was reflecting light like a structured material. To understand why that's strange, imagine shining a flashlight at snow. The light scatters in all directions, soft and diffused. That's what normal comets do. They're random, porous, dusty. Now imagine shining that same light at polished glass or laminated quartz. The beam reflects cleanly at a predictable angle. That's what 3i Atlas was doing from space. So astronomers tried to model it. They simulated thousands of possible shapes, jagged, spherical, lumpy, fractured. None of them matched the real light curve. Then, out of curiosity, a graduate student in Helsinki tried something different. She coded a layered composite alternating strata of ice and nickel-rich material, like concentric shells. And the fit was perfect. The model predicted the same rhythmic brightening seen by Subaru, the same polarization angles seen by the VLT in Chile, even the faint color shifts caught by Hubble's ultraviolet camera. That was the moment the chat rooms lit up. Because the only objects we know of that behave this way are built Of course, no one said that outright, not yet, but the implications hung in the air like static. Could natural processes create a multi-layered, light-directing structure? Maybe. Some crystalline ices in extreme cold can form stratified patterns under pressure. Certain meteorites show micro-layering when molten metals cool in vacuum. But 3I Atlas wasn't showing microscopic layers. Its reflection pattern implied macroscopic order, kilometre-scale symmetry. It was behaving less like a ball of ice and more like a lens. That's when the mirror test was born, a coordinated international effort to probe the comet's optical properties in detail. Observatories across the world aimed every instrument they could spare. Polarimeters measured light polarization. Infrared telescopes scanned for thermal gradients. Even the James Webb Space Telescope diverted time for a brief look. The results were baffling. The comet's reflective index varied too cleanly. In places, it mirrored the spectrum of nickel, in others, carbon dioxide frost. But the transitions were sharp boundaries, so crisp they'd need uniform temperature control to form naturally. One researcher described it as a snowball made of layers so distinct, it's like looking at a geologic core sample built by design. When plotted in 3 dimensions, the reflectivity map reveals something no one wanted to say out loud, a faint but consistent hexagonal symmetry. That single word hexagonal set off a storm. Was it coincidence? Crystals form hexagonal patterns all the time. Snowflakes do. Ice does. Even basalt columns on Earth can take hexagonal shapes as they cool. But those are microscopic or limited to flat planes. What the team found around 3I Atlas was vast, a hexagonal distribution pattern across its surface, repeating over hundreds of meters. If real, it wasn't a coincidence. It was architecture. The data leaked almost instantly. Screenshots of spectral overlays, 3D reconstructions, snippets of internal memos. Within hours, the hashtag number, the mirror test, was trending globally. Podcasters speculated it was hollow, a shell perhaps, or a vessel camouflaged as a comet. Others claimed it was a naturally formed optical resonator, a cosmic kaleidoscope left behind by an ancient star system. But the strangest detail came from Webb's infrared readings. When sunlight hit certain portions of the comet, the emitted heat wasn't diffuse. It radiated from discrete zones, as though only specific areas were warming up. Some called them hotspots, others called them nodes. It was as if parts of the comet were absorbing and redirecting energy deliberately. NASA's silence deepened. No official confirmation, no denial. Only a few quiet data redactions in the archives. That left speculation to fill the void. Had 3I Atlas been misclassified from the start? Was it not a comet, but some kind of relic, a fragment of an ancient megastructure, wandering between stars? Or, more unnervingly, could it still be functioning a dormant probe wrapped in the disguise of ice? In a late-night live stream, astrophysicist Dr. Raphael Koenig summarized the tension perfectly. We're staring at a mirror, and it's staring back. Every assumption we've made about what's natural is being reflected and tested. Maybe this isn't about what 3I Atlas is, but about what we're finally ready to see. His words hit hard. Because that was the truth behind the mirror test. It wasn't just about the comet, it was about us. For centuries, we've told ourselves we'd recognize alien technology if we saw it, that it would look engineered, metallic, sharp-edged. But what if intelligence hides in subtlety, in the geometry of ice, the layering of light, the whisper of symmetry across the stars? What if what we're seeing isn't a message but a reflection? A mirror showing us that the line between artifact and nature, between the built and the born, was never as clean as we wanted it to be. By November 3, Atlas was already fading into the black beyond Jupiter's orbit, but the data remained, the shimmer, the pulses, the impossible reflections. And somewhere in the static of that light, hidden between layers of dust and ice, a question still burns. If this wasn't a comet, then what was pretending to be one? Silence. And that's how it always ends, not with answers, but with the quiet that follows too many questions. As the last glimmer of 3I Atlas faded beyond Jupiter's orbit, Astronomers around the world found themselves staring at a void that suddenly felt fuller than ever before. Because that's the paradox of discovery. Sometimes the further something slips from reach, the closer it gets to meaning. And 3I Atlas, the comet that breathed, left behind more meaning than anyone was ready for. It began, remember, with the impossible water. A frozen traveller from another star system, exhaling 40 kilograms of water every second, far beyond the region where comets are supposed to sleep. It wasn't supposed to move, it wasn't supposed to live, and yet it did. From the first ultraviolet readings, it violated everything we thought we understood about thermodynamics and solar energy. It was alive in its own quiet way, not biologically, but kinetically, defiant against cold and distance. Then came the nickel, bright, unmistakable, and utterly alone. No iron, no twin element to balance the scales of cosmic chemistry. It was like the universe had suddenly coughed up a signature from a place where the rules of formation, the ones that govern every rock, every star, every planet we've ever studied, simply didn't apply. And then cyanide, a whisper of carbon and nitrogen, a molecule synonymous with death, and yet paradoxically, the seed of life. In the vast dark between stars, cyanide can be both the destroyer and the architect. It kills, yes, but it also builds amino acids, the first scaffolds of biology. The comet carried it in abundance, pouring CN molecules into its tail like a warning and a gift all at once. If you were poetic, you might say that 3I Atlas wasn't just leaking chemistry, it was leaking duality. The chemistry of death, the chemistry of life, both born from the same frozen breath. And just when scientists thought they had categorized the unthinkable, the next revelation shattered time itself. 3I Atlas, through isotopic analysis, proved older than our Sunday, older than the solar system that discovered it. Its dust carried the fingerprints of long-dead stars, supernova isotopes that predated Earth, Mars, and every world we've ever known. It wasn't a visitor, it was a survivor, a relic from before our beginning, a message not written in symbols but in starlight. By then, astronomers had stopped asking if 3I Atlas was strange. The question had become how strange, because even its motion refused to obey. Tiny but measurable deviations in its orbit, unaccounted for accelerations that didn't match outgassing pressure or gravitational influence. It was moving in a way that suggested control, or at least coherence, as though something inside it responded to more than physics. When plotted, its path formed an uncanny precision, not random, not chaotic, predictable, almost deliberate. That was when whispers began, guided motion. Not proof of anything artificial, no, but something organized, something we didn't yet have a word for. And while scientists argued, the skies themselves seemed to echo the story. The October alignments, Mercury, Ceres, and the comet crossing a single plane in the heavens. The sudden flare of odd radio circles, immense radio rings blooming in distant space at the exact same time. Coincidence? Probably. But coincidence can feel like choreography when viewed from the right angle. The internet saw patterns, NASA went quiet, and through that silence, a new kind of curiosity spread, not panic, but wonder. Because the unknown is contagious. Then came the mirror test, the discovery that broke even the skeptics. Light scattering data revealed that 3I Atlas wasn't homogeneous at all. It was layered, like a mirror made of ice and metal. The way it reflected light was too structured, too deliberate. The models that matched best weren't of solid rock, but of composite geometry strata, alternating between reflective and absorptive materials, each aligned in hexagonal symmetry. Natural? Maybe. But if nature did this, it did so with a precision we'd never witnessed before. To some, it was evidence of mineral physics we didn't yet understand. To others, it was something more haunting. A message in form rather than signal. Now, months later, as 3I Atlas fades into the cold dark between stars, scientists remain divided. Some say it's simply the most complex natural object we've ever observed, a geological fossil from another solar nursery, carrying chemical quirks from a different era of the galaxy. Others aren't so sure, because every line of data, the breathing water, the nickel without iron, the cyanide, the structured reflection, they all point toward one truth we can't quite name. It's not that 3I Atlas defies explanation, it's that it demands a new one. If it were just chemistry, it would be fascinating. If it were just motion, it would be perplexing. If it were just light, it would be strange. But it's all of it, together. A single object whispering contradictions across every wavelength we have. It doesn't fit into any box we built because maybe it's not supposed to. Maybe it's the box itself that's wrong. In one of the last public lectures before the data went classified, astrophysicist Dr. Sophia Martins, the same one who first noticed the synchronized cyanide pulses, closed her talk with a question that still lingers. If a civilization wanted to leave a message that could outlive its world, its language, its species, what would it write it in? Not words, not sound. Maybe it would write it in chemistry, in physics, in behavior. Something so universal that even 1 billion years later, someone like us would look up and say that's impossible. The audience fell silent, because maybe that's what 3I Atlas is, not an artifact, not a ship, not even a comet. Maybe it's a sentence written in the oldest medium there is matter itself. A fragment of a story that began before we existed to read it. Today, astronomers still argue in journals and conferences their data precise and their conclusions divided. But there's one consensus that's impossible to ignore. Whatever 3I Atlas truly is, it's rewriting the boundaries of what we thought the cosmos could produce. It's forcing us to rethink chemistry, formation theory, and even the timeline of galactic evolution. It's not the end of a mystery, it's the beginning of a new one. So when people ask, what is 3I Atlas? The answer, at least for now, is simple. It's the universe speaking in a dialect of ice and light, of decay and design, of death and creation. And maybe for the first time, we're learning to listen. Because perhaps the universe has never been silent. Perhaps it's been whispering all along, through comets, through dust, through the strange visitors that drift in from the dark. And maybe 3I Atlas isn't a message to us, but a reminder of us. That, in a cosmos built from chaos, even a fragment of pattern, even a whisper of symmetry, means something profound is out there, trying to be known. So we look up, we point our telescopes, we tune our receivers, and we listen. Because the next time the universe speaks, we just might recognize its language.